Okay, so this is problem 8.1 out of Griffith's Quantum Mechanics. And before I solve this problem, if you wouldn't mind liking the video and subscribing, I'd greatly appreciate it. Okay, so problem 8.1, it says use the Gaussian trial function, which I have right here, to obtain the lowest upper bound you can on the ground state of energy A. The linear potential V of x equals alpha, absolute value of x, and V of x equals alpha x to the fourth. So that's our trial function. I have it there. And obviously, when we normalize our wave function, we're going to get the same A that you would get in that example problem. So you can just kind of follow along there to see how you normalize that wave function. Likewise, the kinetic energy term will not change either, because that's not dependent on your potential energy. So we actually don't need to renormalize this wave function, and we don't need to calculate our expectation value of kinetic energy. What we do need to calculate and what changes is our potential energy. So we'll start with part A, and we want to calculate the expectation value of our potential energy. Okay, so in part A, our potential energy is alpha absolute value of x. All right, so what we're going to do, the expectation value is going to be the integral of psi V of x psi dx, and of course there is no imaginary component here, so the psi star is a little redundant, but what we get is the integral of a squared e to the minus bx times e to the minus bx, that's e to the minus 2 bx squared, times alpha absolute value of x dx. Okay, so the trick to this, or one thing that's at least important to note, is our absolute value function is an even function. So this is the integral from negative infinity to positive infinity, but because it's even, we have the trick where we can change this by change our bounds from 0 to infinity if we multiply by 2. So we'll have 2 a squared alpha, and those are all constants, they can come out. And then what are we left with? Well, from 0 to infinity, just have x e to the minus 2b x squared dx. Okay, so now we just have to integrate this, and I think you can just do maybe a u sub and by parts here. If you just plug it into an integral calculator, which is what I'm going to, or what I have done here, you will get something along the lines of minus 1 over 4b e to the minus 2b x squared, evaluated from 0 to infinity. Okay, so now you'll just evaluate this. So we have 2 alpha a squared is 2b over pi to the 1/2 times, and then essentially what you're looking at is what happens for e to the minus x squared, what happens at plus or minus infinity, or positive infinity and 0. So if you plug in positive infinity, let's see, that's e to the minus x, so that's going down, that should go to 0, minus a negative turns out positive, e to the 0 is obviously just 1, so that would be 1 over 4b. Okay, which is the same thing as alpha over 2b times 2b over pi square root. And if you wanted to be really fancy, that's the same thing as, let's see, alpha over 2b pi square root. So that is the expectation value of your potential energy. That's the only thing that's different here. Now we can find the expectation value of our Hamiltonian, which is just the expectation value of your kinetic energy plus your expectation value of your potential energy. Okay, so once again, your kinetic energy is not going to change. H bar squared b over 2m plus this term that we just found, alpha over 2b pi square root. So that's our Hamiltonian. Now what we want to do is take the derivative of our expectation value of our Hamiltonian with respect to the parameter b. We're going to set that equal to 0 to minimize. Okay, so that's going to be equal to, the first term will just be h bar squared over 2m. And then let's see, this term here, just a little scratch work, will be alpha b to the minus 1/2 over 2 pi. So that's just a power rule. That turns into minus alpha over 2 b to the 3/2 2b square root. So minus alpha over 2b to the 3/2 times the square root of 2 pi. And that's all equal to 0. So now I'm just going to move that over. Alpha 2b to the 3/2 times square root 2 pi is equal to h bar squared over 2m. So 2's drop here. And I'm going to multiply over by the b and the m and divide by the h bar squared. So times over 2 pi equals b to the 3/2. Okay, so that's the same thing as the square root of b cubed using our what we know about exponents. So now we can just go ahead and solve for b, and you get m times alpha over h bar squared times 2 pi all to the power 2/3. So now to find the minimum value of your Hamiltonian, we simply plug this b into what we have here. So you're basically just going to plug the b into here and into here. And after you do all that algebra, you should get 3/2 alpha squared h bar squared over 2 pi times m to the 1/3. Okay. And part B will be very similar, only now we have to find a new potential, which is alpha x to the 4th. So let's just do that kind of quickly because it's the same process here. Again, an even function, so 2 alpha a squared, oops, don't know why I was drawing that. Again, now we're going from 0 to the infinity, we're multiplying by 2, and it's an even function, so that's okay. And then we're going to have x to the 4th, e to the minus 2b x squared dx. And again, that's a whole nother integral you can plug in and solve, but you should get 2 alpha a squared times 3 over 8 times 4b squared, which let's see is going to be, let's just drop that to a 2. So alpha a squared 3 over 8 times 2 is 16, 16b squared. Okay, and then you can plug in for your a, and you should get 3 alpha over 16b squared. And then just like before, we write our Hamiltonian as the sum of our expectation value of kinetic energy and potential energy. And again, the kinetic energy term won't be affected by this change in potential. So h bar squared b over 2m plus our new potential of 3 alpha over 16b squared. And then it's just an optimization problem. The derivative of our expectation value of the Hamiltonian with respect to b and set it equal to 0. It's h bar squared over 2m minus 6 alpha over 16b cubed. And 6 over 16, let's see, that's what, 3 over 8? Simplify that a little bit. Okay. So 3 alpha over 8b cubed equals h bar squared over 2m, or 2m over h bar squared times 3 alpha over 8 equals b cubed. That turns into a 4. So we have 3m alpha over 4 h bar squared equals b cubed. And of course you can take the cubed root of that to see that b is 3 alpha m over 4 h bar squared to the 1/3. And then finally all you need to do is plug that b back into our expectation value equation up here. And when you do that, you should get, that's just plugging in and simplifying, 3/4 times 3 alpha h bar to the 4th over 4m squared, all raised to the 1/3 power. So hopefully it's okay if I don't show that. You guys are good with that. And if this video helped at all, please like and subscribe. I'd really appreciate it.